The race to return to the moon is still on. Or is it? For more than 50 years, the footprints left behind by the 12 astronauts of the Apollo missions have remained untouched on the lunar surface, perfectly preserved as a symbolic trophy of Cold War competition. Under NASA's Artemis program, the goal was to return there by 2024, and this time not merely to leave footprints, but to stay. Since then, the schedule has slipped somewhat, but Artemis I, the uncrewed mission designed to test the SLS rocket and Orion spacecraft, finally launched on November 16, 2022. Its successor, Artemis II, was originally scheduled to launch in February of this year. But here's the thing, it still hasn't left the ground. In fact, it remains sitting on the launch pad. No new footprints have appeared on the moon yet. So what is happening with NASA's Artemis program? Will the second phase launch anytime soon? Or are more serious problems beginning to emerge beneath the surface? Join me today as we take a closer look behind the scenes of the Artemis program. From the technical issues currently delaying Artemis II to the unexpected announcement that Artemis III may no longer land on the moon, we'll explore the science, engineering, and strategy behind humanity's return to the lunar frontier. Will we actually make it back? Artemis is arguably the most ambitious engineering project ever undertaken by humanity, with the goal of establishing a permanent and sustainable presence on another world. Yet standing on the threshold of this new era, the road ahead appears to be becoming increasingly complicated. First announced in 2017, the program was intended to become NASA's flagship initiative for the following decade, aiming in many ways to revive, and perhaps even surpass, the achievements of the Apollo program of the 1960s. Back then, it took humanity only 8 years to reach the moon. With all of today's technological advances, a second attempt should have been easier, but that has not been the case. 9 years have passed since the first announcements, and we are still far from the finish line. NASA's immediate priority is Artemis II, the first crewed mission to travel to the vicinity of the moon since 1972. Its objective is not a lunar landing, but rather the validation of life support systems, navigation, communications, and deep space safety procedures. The 10-day mission, crewed by Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, was initially expected to launch in early 2026. Since then, however, it has encountered a series of technical delays, pushing the launch window from early February to March 6th, and then to no earlier than April 1st. Why? To understand that, let's examine the timeline of events. On January 17, 2026, the Space Launch System, SLS rocket and Orion spacecraft were rolled out to Launch Complex 39B in preparation for an early February launch attempt. That phase went smoothly, but it was also where most of the good news ended. Nearly 2 weeks later, the first wet dress rehearsal, a full fueling test and countdown simulation, was conducted. Although it was not a complete failure, engineers detected a liquid hydrogen leak during fueling operations. Hydrogen is the smallest molecule in the universe, and at the extreme temperatures required for flight operations, -252 degrees Celsius, containing it is notoriously difficult. The leak was therefore not entirely unexpected. Nevertheless, a vehicle cannot launch with such a flaw. Engineers were forced to replace seals and a filter within the ground support system. The first setback had arrived. The second wet dress rehearsal, completed on February 19th, proved far more successful. Teams loaded approximately 2.6 million liters of liquid hydrogen and liquid oxygen into the rocket's stages and carried out 2 practice countdowns. No leaks were detected, and the vehicle was declared ready for launch. But not for long. After the tests, during a routine purge and repressurization procedure, engineers discovered that helium was not circulating properly through the interim cryogenic propulsion stage, ICPS, the upper stage of the SLS rocket. Helium is critical for rockets of this type. It is used to maintain pressure in the propellant tanks and to purge the fuel lines. A leak puts the entire mission at risk because, without proper pressure management, the propulsion system cannot function as intended. Engineers eventually traced the problem to a faulty seal and a malfunctioning check valve. However, Because the issue was located in a section of the rocket that could not be accessed on the launch pad, NASA was forced to return the entire 98-meter-tall vehicle to the Vehicle Assembly Building for repairs. These repeated leaks were more than just an inconvenience. In many ways, they pointed to a larger problem. More technology is not always better. The Artemis program contains far more components that can potentially fail than the original Apollo missions, and those systems are not launched very frequently. In November 1967, Apollo 4 became the first flight of the Saturn V rocket. Less than 2 years later, Apollo 11 carried humans to the moon. By comparison, the SLS last flew during Artemis I in 2022, and at the time of writing, nearly 4 years had passed. NASA Administrator Jared Isaacman has noted that launching a rocket as complex as the SLS only once every few years can lead to a degradation of skills among the workforce. In other words, teams do not get enough hands-on practice, which can contribute to mistakes and inefficiencies. To address this, NASA has proposed a new plan: increase the launch cadence to roughly once every 10 months. The goal is to keep both the hardware and the teams mission-ready, but that future is still some distance away. First, Artemis II has to get off the ground and head beyond Earth. Beyond the technical issues and NASA's cautious hints about skill erosion, a deeper and more unsettling reality is emerging: the sheer level of risk involved in what we are trying to accomplish. More than 50 years have passed since a crewed spacecraft last left Earth orbit and headed toward the Moon, and recently, NASA officials have faced criticism for avoiding direct questions about the possibility of mission failure, or, more bluntly, loss of life. During the Apollo era, humanity was stepping into the unknown, and the outcome was considered worth extraordinary risk. Today we know that it can be done more safely, so the threshold for acceptable risk is much lower. The truth is that returning humans to the Moon for the first time in 54 years is inherently dangerous. We are relying on new software, new contractors, and a rocket that has flown only once. Although Artemis I was widely regarded as an outstanding test flight, it still revealed anomalies that could have been catastrophic on a crewed mission. NASA is therefore balancing political pressure to maintain the schedule against the reality that any major accident could threaten the entire program. After 2 scrubbed launch attempts, the uncrewed Artemis I mission finally lifted off from Cape Canaveral, Florida, on November 16, 2022. It was the first time the SLS rocket and the Orion spacecraft left Earth together. The mission lasted 25 days and 10 hours before Orion safely splashed down back on Earth. As mentioned earlier, it was a major success and demonstrated that we could once again send a spacecraft capable of carrying humans to the Moon and back. The European service module performed even better than expected. Its solar arrays generated so much surplus power that engineers used them to capture iconic images of Orion with Earth in the background, effectively turning the spacecraft into its own selfie stick. Yet it was only after the mission had concluded that the anomalies began to reveal themselves. One of the most critical issues involved Orion's heat shield, specifically how it behaved during re-entry into Earth's atmosphere at speeds approaching 40,000 kilometers per hour. Post-flight inspections revealed that the ablative material covering the shield, known as avcoat, had cracked, chipped, and broken away in more than 100 locations. Even more concerning, this type of damage had never been observed during the Apollo era, despite the use of the same material. The heat shield is what separates fragile human astronauts from the extreme temperatures generated during atmospheric re-entry, and portions of it were simply breaking off. NASA's investigation found that gases produced by intense heating during re-entry were becoming trapped inside the avcoat material. Under normal circumstances, these gases escape through the charred outer layer. However, because the material was not sufficiently permeable, pressure built up internally until sections of the shield literally fractured. If the damage became severe enough, it could potentially lead to the complete loss of the capsule, a risk that is unacceptable when human lives are on board. Based on these findings, NASA made a somewhat controversial decision. Rather than redesigning the heat shield itself, the agency chose to modify the way astronauts returned to Earth. During Artemis I, Orion used a skip entry maneuver in which the capsule briefly enters the atmosphere, bounces back out like a stone skipping across water, and then re-enters again, gradually shedding speed. While this approach reduces G-forces on the crew, it also appears to worsen the heat shield issue because gases continue accumulating during the skip phase. For Artemis II, NASA has decided to eliminate the skip. Instead, Orion will perform a steeper and more direct atmospheric entry. Although this will subject astronauts to greater physical stress, it is considered safer for the heat shield and ultimately safer for the crew. A little extra discomfort is a small price to pay if it improves their chances of returning home safely. It is a significant change to the mission profile, but it is far from the biggest surprise to emerge from the Artemis program in recent months. From the beginning, the Artemis roadmap seemed fairly straightforward. Artemis I would prove that the rocket and spacecraft could reach the moon. Artemis II would add a crew and validate all remaining systems during a lunar flyby. Artemis III would land humans on the moon. For nearly a decade, Artemis III was promoted as the Grand Return, the mission that would once again place human footprints on the lunar surface. But by February 2026, that plan had been abandoned. Artemis III would no longer attempt a lunar landing. Instead, the mission was redefined as a comprehensive 30-day test campaign in low Earth orbit. The reasoning behind this decision comes down to safety and complexity. An independent safety review concluded that the original mission architecture carried what it described as an accumulated technical risk. To land on the moon, the Orion spacecraft must first dock with SpaceX's Starship human landing system, the vehicle intended to carry astronauts from lunar orbit to the surface. This rendezvous must occur in a highly specific lunar orbit. However, Starship is an enormous spacecraft that requires more than a dozen tanker launches to refill its propellant tanks before departing for the moon. NASA ultimately concluded that attempting a lunar landing while simultaneously relying on so many first-time operations, such as the first crewed docking, the first large-scale cryogenic fuel transfer, and the first operational use of next-generation lunar spacesuits, was not the wisest approach. Instead, Artemis III has been reassigned a role similar to that of Apollo 9 in 1969, remaining close to Earth to thoroughly test the lunar lander and related systems before committing them to a mission all the way to the moon. In 2027, Artemis III is planned to perform a docking operation between Orion and either SpaceX's Starship lunar lander or Blue Origin's Blue Moon lander while in Earth orbit. This approach allows engineers and astronauts to thoroughly test life support systems, communications, and docking procedures without facing the life or death risks associated with operating nearly 390,000 kilometers away from Earth. These mission revisions are accompanied by major changes to the rocket itself. For years, NASA intended to upgrade the Space Launch System to the more powerful Block 1B configuration, featuring a new upper stage known as the Exploration Upper Stage, EUS. However, the EUS program faced persistent criticism due to schedule delays and escalating costs. Under the leadership of Jared Isaacman, NASA ultimately canceled the EUS program along with the planned Block 1B and Block 2 upgrades. Instead, the agency selected United Launch Alliance's Centaur 5 upper stage as the future upper stage for SLS, beginning with Artemis IV. Centaur 5 is a dual-engine stage already flying on the Vulcan rocket and serves as a near off-the-shelf replacement, eliminating the need for the costly development of the EUS. Although it carries roughly twice as much propellant as the current ICPS, Centaur 5 remains compatible with the existing ML-1 mobile launcher, removing the need to build entirely new launch infrastructure. NASA hopes that this standardization will help eliminate the current 3-year gaps between launches and move toward a more sustainable flight cadence of one mission approximately every 10 months. This brings us to the key question. If Artemis III is now essentially a full-scale rehearsal in Earth orbit, when will astronauts actually return to the lunar surface? Unfortunately, the answer requires a bit more patience. The current target for Artemis IV and the next lunar landing opportunity is early 2028. That said, the scientific value of the mission's destination near the moon's south pole is extraordinary and may justify the wait. Unlike the Apollo landing sites near the lunar equator, Artemis IV is expected to target the Moon's south polar region, a landscape of permanent darkness and extreme environmental conditions. Because the Moon's rotational axis is tilted by only about 1.5 degrees, sunlight remains low on the horizon, creating shadows that have persisted for billions of years. These regions are known as permanently shadowed regions, or PSRs. Inside some of these craters, temperatures can plunge to around -240 degrees Celsius, making them colder than the surface of Pluto. This is where the 21st century's lunar gold rush begins, the search for water ice. Scientists already know that these dark craters act as natural cold traps, preserving ice likely delivered by comets and asteroids billions of years ago. And this is far more than a scientific curiosity. It could become a critical strategic resource. If that ice can be extracted, it could be separated into oxygen for breathing and hydrogen for rocket fuel. In that scenario, the Moon could eventually function as a refueling station for deep space exploration, becoming a crucial stepping stone toward future missions to Mars. Artemis IV will carry a suite of advanced scientific instruments designed to investigate this region. One of the most important is DUSTER, the Dust Environment and Plasma Explorer. Lunar dust is considered one of the greatest hazards facing future explorers. Unlike dust on Earth, it consists of microscopic, razor-sharp fragments of volcanic glass that become electrically charged by the solar wind. It clings to equipment, damages seals, and can be hazardous if inhaled. Mounted on a small autonomous rover known as MAPP, DUSTER will study how lunar dust behaves during spacecraft landings and astronaut surface operations. Working alongside it will be the South Pole Seismic Station, SPSS, a sensitive seismometer designed to listen to the Moon by measuring moonquakes and monitoring the frequency of meteorite impacts. Astronauts will even use a thumper device, an instrument that generates controlled seismic waves, to probe the subsurface beneath their feet, searching for signatures of hidden ice deposits. One of the key regions of interest is Shackleton Crater, 21 kilometers wide and 4 kilometers deep, a place where the crater walls are so steep they exceed a 30-degree incline, creating an ideal trap for ancient volatile compounds. To operate in such an environment, astronauts need more than just a rocket. They need a new skin. The next generation of explorers will wear the Axiom Extravehicular Mobility Unit, AXIMU, spacesuits. Developed in collaboration between Axiom Space and even the fashion house Prada, these suits represent a major leap forward compared to NASA's Apollo-era A7L suits. The Apollo suits were notoriously rigid. Astronauts often had to move in a bouncing gait because bending at the knees or waist was extremely limited. The AXIMU, by contrast, uses a hybrid architecture of hard structural elements and advanced flexible fabric joints, enabling a range of motion never before achieved in pressurized suits. In effect, this suit is a self-contained spacecraft. It includes a life support system capable of sustaining astronauts in the extreme cold of permanently shadowed regions, PSRs, for at least 2 hours. It also integrates 4G/LTE communications developed in partnership with Nokia, along with a high-tech visor system created with Oakley. Most importantly, it features specialized seals and materials designed to prevent abrasive lunar dust from infiltrating joints and airlock systems. Artemis III will mark the first time these suits are tested in the actual vacuum of space prior to their use in a lunar landing planned for 2028. But beyond all this exciting science, another force is shaping the race back to the Moon: geopolitics. Despite rising costs and the pressure to demonstrate progress toward returning humans to the lunar surface, NASA's urgency is also driven by what is increasingly described as real competition from China. Beijing has been steadily achieving key milestones, including the delivery of samples from the Moon's far side and the announcement of its own crewed lunar landing plans for around 2030. U.S. officials are increasingly concerned about a potential space domain takeover scenario, in which China could establish a foothold in the resource-rich lunar South Pole region and effectively assert strategic dominance there. If that were to happen, NASA's plans for future Mars missions and beyond could begin to unravel like lunar dust. This has transformed Artemis from a purely scientific endeavor into a strategic imperative to win a broader space race. Only time will tell who ultimately comes out ahead. The journey to the moon has always been a story of trial and error. In 1969, we reached its surface because we were willing to take enormous risks in a race against time and the Soviet Union. Today, the stakes are different. We are no longer competing just to plant a flag, we are competing to build an economy. The transition to a standardized SLS rocket with the Centaur 5 upper stage, the Artemis III test campaign in low Earth orbit, and the deep scientific objectives of Artemis IV all point toward a shift to sustainable, repeatable exploration. Simply returning humans to the moon is no longer enough to win the geopolitical competition.